In today's video, we're going to look at the definition of the determinant. In the upcoming videos, we will look at two methods of evaluating a determinant and look at an application of the determinant, which is known as Cramer's rule. And this allows us to solve a system of linear equations with a specific condition by using determinants instead of row reduction. So determinants first arose in the study of solutions of linear systems. As was mentioned, one type method is known as Cramer's rule. However, these methods are not as efficient as the method that we had previously studied using row reduction. We will be using determinants later when we study linear transformations, and more importantly, when we study the eigenproblem. Now, before we can define what a determinant is, we need another concept. This is the concept of a permutation. So we let S be the set of integers 1, 2 through n arranged in ascending order. A rearrangement of these elements, j sub 1, j sub 2, yada yada yada, j sub n, is called a permutation of the set S. So when you rearrange the elements of a set, it's known as a permutation of that set. We can consider a permutation to be a one-to-one mapping of S onto itself. Now, we say that a permutation has an inversion if a larger integer precedes a smaller one in the permutation. Permutation is called even if the total number of inversions in it is even, or odd if the total number of inversions in it is odd. The number of permutations a set S of n elements has is 2 to the n, with exactly half of them being even and the other half being odd. So if we look at a set of 4 elements, it will have 2 to the 4th, which is 16 permutations. 8 of them will be even, and 8 of them will be odd. So we have the set 1, 2, 3. We want to determine all permutations and include the number of inversions of each permutation, determining which are even and which are odd. So a simple way that I like to do this is start with the first element in the set and then draw a tree. All right, so from 1, we can then have 2, or we can have 3. Right, then from 2, we only have one option left, 3. And from 3, we only have one option left, which is 2. Now repeat this for the elements 2 and 3. And if we just follow the path of each one, we have our inversion, our permutations. So let's create a table. First row will be the permutation. Second will be number of inversions. And the final will be whether it is even or odd. First permutation is the set itself. 1, 2, 3. Obviously this has 0 inversions, which makes it even. Next up, we have 1, 3, 2. Now 3 precedes 2, so we have one inversion, making this permutation odd. Next we have 2, 1, 3. Again, 2 precedes 1, so we have one inversion, making this permutation odd. Next, we have the permutation 2, 3, 1. So 2 precedes 1 and 3 precedes 1. We have two inversions, making this even. Next, we have 3, 1, 2. So 3 precedes 1 and 3 precedes 2. This gives us two inversions, making this even. And finally, we have 3, 2, 1. Right, so 3 precedes 2, 3 precedes 1, and 2 precedes 1. This gives us three inversions, making this permutation odd. Now let's just make sure that we have the correct number of permutations, the correct number of even, and the correct number of odd. All right, so S has 3 elements, so we should have 8 permutations. 1, 2, 3, 4, 5, 6. So my apologies. This should not be 2 to the n. I was thinking of power set, not permutations. We should have n factorial. All right, so 3 factorials, 3 times 2 times 1, which is 6. So we do have the correct number of permutations there. Since we have 6, we should have 3 that are even and 3 that are odd. 1, 2, 3 even, 1, 2, 3 odd. So that is correct. So here we have a list of all the permutations, how many inversions each permutation has, as well as which are even and which are odd. Now that we have the idea of permutations down, we can define the determinant. So let A be an n by n matrix. So it's important. The matrix that we are dealing with is a square matrix. The determinant is a function. So the determinant function, which is denoted by det, is defined to be the determinant of A is the sum plus or minus a1j1, a2j2, so on and so forth, an jn, where this summation is over all the permutations of the set 1 to n. The sign is taken as plus or minus according to whether the permutation is even or odd, respectively. So if your permutation is even, it's a plus sign. If the permutation is odd, it is a negative sign. Right now, in the function, notice that the row subscripts are in the natural order, that is, in ascending order, 1, 2, 3, 4, up to n. The column subscripts are in the order of the permutation that you're using. We will now use this definition to derive a formula for a 2 by 2 determinant and a 3 by 3 determinant. Starting with the 2 by 2. Let's call that matrix A2 to represent a square matrix of order 2. All right, so we have a total of 4 entries, A11, A12, A21, and A22. Okay. Now our set is just 1, 2. So we should have 2 factorial permutations, which is just 2. And they are 1, 2, and 2, 1. So 1, 2 has no inversions, makes it even. 2, 1 has a single inversion, makes it odd. So by the definition, determinant of A, start with the first permutation. It is even, so we have a plus sign. A, 1, 1 times A, 2, 2. Now we're going to use the second permutation. It is odd, so we get minus A, 1, 2, A, 2, 1. So this is our formula for a 2 by 2 determinant. And notice what's happening. To actually evaluate this determinant, what we're doing is A11 times A22, then minus in the opposite direction A12 times A21. Right, so we kind of do cross. As we move from left to right, it's positive. As we move from right to left, it is negative. Let's now set up our 3 by 3 matrix. We'll call this A sub 3. Right, first row, A11, A12, A13. Then we have A21, A22, A23. Then we have A31, A32, and A33. I should now have drawn the vertical bars. That represents a determinant. I meant to actually draw the matrix. Right at the permutations, well, we already did this, right? This was the first example. I'm not going to rewrite them, so let's just say, therefore, the determinant of A So we're going to use the first permutation, which is even. Then we have two odds, then two more evens, and then an odd. Just for aesthetics reasons, let's do all the positive terms first. So first, we will use this permutation. Next one we'll use is that. Then the third one we'll use is that one. All right? First, the permutation 1, 2, 3. So A11, A22, A33 plus, right? Next 2, 3, 1. So A12, A23, A31 plus final permutation for the positives 3, 1, 2, A13, A21, A32. Right now, notice what's going on here, right? If we just look at the positives, A11, A22, A33 goes like this. A12, A23, A31. Right, so A12, A23. And if you think of this like the asteroids game, where once you leave one side, you re-enter the other, we can come down here and say A31. Then finally we have A13, A21, A32. So that kind of goes like this. Now what we want to do is let's use the three odd permutations. So the next term will be minus, and we'll use this permutation. Then it'll be minus, we'll use that, and then minus, we'll use the final. So 1, 3, 2. So minus A11, A23, A32. Next, 2, 1, 3. I'm going to move down. So minus A12, A23, A32. And finally, 3, 2, 1. So minus A13, A22, A31. And again, notice 1, 1, 2, 3, 3, 2. Minus as we're going to the left. Right? So 1, 1, 2, 3, 3, 2. 1, 2, 2, 3, 3, 2. 1, 2. That should have been 2, 1, and then 3, 3. My apologies. 2, 1, and 3, 3. So 1, 2, 2, 1, 3, 3. And finally, 1, 3, 2, 2, 3, 1. 1, 3, 2, 2, 3, 1. So this is our formula then for the determinant of a 3 by 3 matrix. We will end by looking at two properties. First, if A is a matrix, then the determinant of A is equal to the determinant of A transpose. So if you transpose a matrix, you do not change its determinant. So to prove this, we define the matrix A as Aij and the matrix A transpose as Bij, right? Where Bij is Aji, right? It's the transpose. So you just flip column and row. What we then have is take the determinant of A transpose. Right? So this will be the sum plus or minus B1J, 1, B2, J2, so on and so forth, Bn, Jn. Flipping the B's, we get plus or minus A, J11, A, J22, so on and so forth, A, Jn, N. Right? But we can write this term, A, J11 times A, J22 times dot 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 times A, J3, Jnn. This way, we can say it's A1K1, A2K2, ANKN, which is a term in the determinant of A. So each term in determinant of A transpose and the determinant of A are identical. All we have to do now is show that the signs of corresponding terms are identical. So it is known from the study of abstract algebra that number of inversions in the permutation K1, K2, Kn is the same as the number of inversions in the permutation J1, J2 through Jn. I will not go over this in this series. If you're interested, pick up any text in abstract algebra and you can see a proof of this. Therefore, the sign of A1, K1, A2, K2, AN, Kn is equal to the sign of A, J11, A, J22, A, Jn, N. And of course, remember that is B1, J1, B2, J2, up through Bn, Jn. So these two together says that the determinant of A and the determinant of A transpose are the same because they have the exact same terms and the corresponding terms have the exact same sign. All right, final property we will examine in this video. If a row of A consists entirely of zeros, then the determinant of A is 0. So what we're going to do is we're going to say let the ith row of A consist entirely of zeros. So the ith row is our 0 row. Now, since each term of the summation plus or minus A1, J1, A2, J2, so on and so forth, up through AN, JN, contains a factor. Well, I shouldn't say factor, contains an entry from the ith row each term in our determinant will be 0 because if you multiply any number by 0, you get 0. So you're multiplying a bunch of numbers. Somewhere in there is going to be a times 0, so the whole thing goes to 0. So what we're doing is we're just summing a bunch of zeros. So therefore, the determinant of A is equal to 0. And that will conclude this video on an introduction to the determinant. Right, so all we did in this video was define what a determinant is by use of permutations, and we derived two formulas, one for the 2x2 determinant, one for the 3x3 determinant, and looked at two properties. In the next video in this series, we are going to look at one method of evaluating a determinant known as reduction to triangular form. So as always, thank you for watching. I hope you enjoyed, and I will see you all in the next video.